For the custom geometry optimization tutorial, we'll start by opening our Ubuntu terminal and pasting the command to set up our project directory and open Windows Explorer. Next, we need to prepare our input files. Here we have the cell and parent file. Notice the task is set to geometry optimization and the cutoff energy is specified at 570 eV. Now let's navigate to our project folder. In the file explorer, you can see it's currently empty, so we'll copy our prepared cell and parameter files into this directory. Once the files are moved, let's open the cell file. We need to define our lattice parameters and atomic position. I'm also setting the external pressure to 300,000 for this specific calculation. Next, double-check your parent file to ensure the task is correctly set to geometry optimization and the exchange correlation functional is set to PBE. Now we are ready to run. In the terminal, enter castab.mpi followed by your file name. In this case, we use BATO3. This will initiate the calculation using MPI for parallel processing. While that runs, you can refer to the castab documentation for specific command flags. Once the job finishes, use the grep command to check if the geometry optimization completed successfully. If successful, you'll see the final configuration details including the optimized real lattice parameter and unit cell volume. Now that our geometry optimization is finished, I'm going to clear out the terminal so we can start fresh from the band structure calculation. First, I'll jump into my file explorer. I'm heading into my home directory on the Ubuntu server and navigating to my project folder. I need to make sure all my input files from the optimization are ready. I'm moving over to my dedicated band structure folder. I'll open up the cell file using Notepad because we need to make specific adjustment for this run. I'm scrolling down to find the pressure settings. Since we are testing high pressure conditions, I'm going to the external underscore pressure block. Here, I'm updating the value to 300,000. Once that's set, I'll save the file and head back to the terminal. Now let's get the calculation running. I'll input the castab command to start the process. This might take a moment, so while it runs, I usually check the castab documentation if I need to verify any symmetry point or key path settings. Once the main calculation wraps up, it's time to process the data. I'm running the dispersion tools now to convert that raw data into a format we can actually visualize. Now the data process is done. I'll open up Grace to view the plot. It looks a bit messy at first, so I'm going into the axis settings to clean things up. I'm just adjusting the labels and scaling the energy range so the bands are clearly visible. And there we go. That is our final band structure at 300,000 atmosphere. Now looking at the result, at 300 GPa, we can see a significant modification of the electronic states. Notice the band gaps here. It has significantly narrowed compared to the ambient pressure phase. In fact, under this extreme pressure, the valence and conduction bands are moving closer, suggesting the material might be transitioning toward a metallic state or a much narrower semiconductor. This shift is a direct result of the reduced lattice volume forcing greater orbital overlap. Thank you.